Hello everyone, I'm Jieming Ye from Peking University. My report is Domain Generalization Complexity Enhancement for Binary Neural Networks. This is a joint work with Shumao Nan and my advisor Professor Shiliang Zhang. This is the outline of this report, so let's start with the introduction. We review some related works. In 2015, BNN proposed straight-through estimator for gradient approximation, which helped BNNs train in an end-to-end manner. Then, XNORNet, ABCNet, BioNet proposed to apply better network structures to increase the network accuracy. In 2019, CIBCNN used reinforcement learning to mine channel-wise interactions and bring substantial performance gains over the baseline. In 2020, DGRL optimized both BNN structures and chaining strategies to achieve comparable performance with real-value network. Recently, IECU paid attention to the weights in the tails of the distribution, which are hard to optimize to further boost the BNN's performance. However, previous BNNs was mainly focused on increasing the performance in the same domain, but overlooked the generalization complexity of BNNs. Domain generalizations aim to enhance the network performance on out-of-domain data. They can be divided into three categories of methods. Firstly, data manipulation. This kind of methods use methods such as GAN, ADAIN, to do data augmentation or data generalization. Secondly, representation learning methods aim to learn domain invariant representation through aligning features of different domains. Thirdly, DG was also studied in general machine learning paradigm, using ensemble learning, meta learning, or other learning strategy to improve the performance. However, previous DG methods are based on real-value networks and it's hard to transfer to BNN. As we all know, domain generalization complexity enhancement is important for both FNN and BNN. While binary compression significantly accelerates the inference of FNNs, it raises a question that what negative effects will such heavy compression bring to FNNs? We compare the out-of-domain and in-domain performance of BNNs and FNNs. Results shows that the binary compression degrades model robustness to domain shifts. A flat minimum in parameter space can absorb this turbulence brought by domain shift and increase the DG complexity of a network. Therefore, we motivated to optimize the distribution of BNN's weights to choose a flat minimum. However, they cannot be directly adopted to BNNs because of the discrete value in BNN weights. To address this issue, we optimize a real value FNN to purchase a flat minimum. Meanwhile, optimizing weights in FNN to make each of them get close to 1 and -1. BNN activation may suffer from quantization errors during binarization. Binarized activation should also be evenly distributed between -1 and 1 to enhance their complexity in encoding meaningful clues. Therefore, we motivate to optimize the distribution of activations. At this section, I will describe our approach. We further show the overview of our method. LB denotes the task loss calculated using binary weights W. LF denotes the task loss calculated using real value weights with turbulence to find a flat minimum. LG is a gap loss to measure the distance between binarized weights W and real value weights W hat. It is minimized to preserve the flat minimum of W hat in binary weights. LA denotes the activation regularization loss to optimize the distribution of activations. Alpha, beta, gamma are the weights for loss functions. The following parts present details of chaining procedure. To chain the BNN in an end-to-end manner, real value weights W hat n are hence stored at latent weights for gradient accumulation. The chaining strategy is commonly known as straight-through estimator. LB is calculated on outputs computed by binary weights. It's difficult to directly seek flat minimum on BNNs because of the discrete parameters. We found that flat minimum for real value weights instead as follows. Random Gaussian distribution delta is applied in weights using the following formulation. Finally, we minimize the distance between W and W hat to preserve the flat minimum. BNN binarized activation before convolution, which leads to concatenation errors and considerable information loss. To enhance the DG capacity, we propose E to decrease concatenation error in BNN activations. Also, binary activations should be evenly distributed between 1 and -1 to enhance their capacity in encoding meaningful clues. We then propose G to minimize the mean of each pixel. Notice that minimizing the regularization loss equals to maximizing the variance at each location of the activation over the chaining batch. The next section is for experiments. We follow previous domain generalization works to conduct experiments on 3 datasets, PACS, VLCS, and Office Home respectively. In this part, we first compare our methods with existing BNNs and DG methods on PACS. We report the performance of the real value ResNet AT in the table. Currently, there is no DG methods working on BNNs. We first compare different BNNs methods on this task. We also applied different DG methods designed for real value networks on BioNet. Results show that these DG methods do not boost the DG performance of BioNet. Applying LA or LG and LF to BioNet brings performance gains. Our methods combine these laws and achieve the best performance, which outperforms BioNet by 3% in accuracy. Our methods also outperform other BNN's methods and also boost the performance on ReactNet. As shown in the figure, the distribution of weights in BioNet shows one peak around 0. This turbulence of latent weights trained by our methods show 2 peaks. It's easy to infer that latent weights near 0 are sensitive to this turbulence. It means that a small turbulence easily changes the binarized weights. Weights learned by our methods are more robust to this turbulence and product smaller quantization errors after binarization. We further quantify BNN stability by measuring the Seinfeld weights, which also show that our methods is more robust to noise turbulence as shown in the following figures. To further evaluate the effectiveness of our methods, we conduct experiments on dataset Office Home and VLCS and summarize the comparison respectively. On these datasets, we can get similar conclusion as on PACS. We also evaluate our methods on CIFAR 100 and ImageNet. Our methods achieved the best accuracy on CIFAR 100, outperforming recent methods. Our methods achieved comparable performance with ReactNet and outperform other competitors in respect of both accuracy and efficiency. So in conclusion, we discovered that BNNs present degraded DG capability compared with FNNs. We then optimize both distribution of weights and activation to enhance the DG capability of BNNs. Extensive experiments show that our methods show better performance comparing with recent DG methods and BNN methods on different network architectures on both DG and traditional datasets. That's all. Thank you for listening. Our paper and code are available